In this video, I'm going to run through the concept of half-life and then take a look at two half-life questions involving calculations around radioactive decay. Let's start with a basic definition of what half-life is. Now, half-life, it doesn't only apply to radioactivity, but also in chemistry, in medicine, in pharmaceuticals, and it's just basically the time taken for half the substance to decay. Now, in the case of radioactivity, one of the definitions is the time taken for half the radioactive isotopes to decay. So the time taken for half the radioactive isotopes to decay is one definition. Another one is the time taken for the count rate to reduce by half. What does this definition actually mean? So T half is sometimes, as it's abbreviated, subscript half. So what does it actually mean? How can we understand this phrase, time taken for half the radioactive isotopes to decay? Let's just say let's do it in terms of mass, right? Let's pretend we had a substance X and it had a mass of 50 grams, and that was decomposing over time to 25. So the time taken for it to decompose from 50 grams to 25 grams would be considered one half-life. And then the time taken for it to decompose from 25 to another half, 12.5 grams, would be another half-life, and so on. Now, that's the first point to mention. The second point is that for a particular substance, in this case, a radioactive isotope, the half-life is constant. So it's always constant. So for radioactive isotopes, it can vary wildly. So some could be within a few minutes for some isotopes, and others could take years and years, months, weeks. It really does depend on the isotope. It's completely different from isotope to isotope. Also, radioactive decay is random, so you cannot predict which actual isotopes from a sample will decay. Here is the first question. A radioactive element has a half-life of 68 days. After 1020 days, it has a count rate of 45. What was the original count rate? So I'm going to show you two ways to do this, the long way and the shorter way. I'd say the longer way is more sort of intuitive and easier to understand, and then the shorter way is just mathematically quicker. So basically, we have a sample of this element, which is this box here, and the count rate is question mark. And then after 1020 days, the count rate is down to 45. We need to work out how many half-lives have actually taken place in 1020 days. So the first thing to do is to work out how many half-lives have passed. So that's quite simple. You just do 1020 days divided by 68 gives us 15. There has been 15 half-lives that have taken place. Now this is the long way. That goes to that. So there's the first, there's the second, there's the third, fourth, 15th. And we know at that point there that the count rate is 45. Like I said, everyone, this is the long way of doing it, but it's for your understanding before I show you the shorter way. So we've got to find out what that question mark is. So in other words, we've got to work backwards. We know that if we just start there, for example, that if the count rate was 45 after the 15th half-life, then if we go back one place, it would be 90. And then if we go back another place, it would be 180. In other words, you just keep doubling the half-life until you get back to the answer. So that's going to take some time to do. So the quick way to do it is you look at the number of half-lives that have taken place, which is 15. You raise that as a power of 2, so 2 to the power of 15, and then you times that by the count rate 45. Gives an answer of, so the answer is therefore, if I just underline that in blue, is going to be D. Second question. Plutonium-238 is used in a spacecraft to provide heat to power generators. One of these generators contains 925 grams of 238 when it is manufactured. 1 gram of 238 has a power density of 0.54 watts per gram. Plutonium has a half-life of 87.7 years. Calculate the average energy released per second by the generator after 263 years. So we've got this plutonium source. It's decayed by some amount, and we want to know how much energy it has after 263 years. Before I get into this question, I need to define what W means. W is watts. So you may have seen that in electricity content. And basically, 1 watt is equal to 1 joule per second. So if you had a 500 watt, say, hairdryer, that would be 500 joules of electrical energy turned into heat energy every second. So we know that it has 0.54 watts per gram. So 0.54 joules of energy per gram. The first thing we need to do is, quite similar to the other one, is to work out how many half-lives have passed. That is found by taking the total amount of time that's passed, 263, then you divide it by the half-life for this plutonium sample, which is 87.7, and then that gives us 2.99885. I'm taking the full number off the calculator. So that's roughly 3 half-lives. I am going to use the sort of box method I did previously because it's only three drawings. The original amount was 925 grams, and we need to half it once, twice, 3 times. 925 divided by 2 gives us 462.5. Then you divide by 2 again, gives us 231.25. And then the answer in red, you divide by 2 again, gives us 115.625. So that's how many grams of this plutonium substance is remaining after 263 years. Finally, to work out the energy released, we use the number supplied, that there is 0.54 watts in 1 gram. But we don't have 1 gram, we have 115.625 grams. So all I have to do is times 0.54 by 115.625, a simple ratio basically, gives us 62.43 watts. So to 1 decimal place gives us, so this question I think is difficult because it's drawn on some knowledge from electricity. And you've got to understand what power is. Power is measured in watts, and 1 joule per second is 1 watt. You may have seen this formula, P equals IV, power equals current times voltage, which is not related to this question, but power can be thought of in a different context to sort of electrical circuits.